In section 6.2, we're going to look at the indefinite integral and constructing antiderivatives. So we're going to find antiderivatives of basic functions, apply properties of antiderivatives, and then use these to compute definite integrals. We're going to use indefinite integrals and definite integrals and look at the relationship between them. So let's start talking about the indefinite integral. The indefinite integral of a function f is the set of all antiderivatives of f. And we denote that with the integral symbol f of x dx. It's the same notation as the definite integral without the bounds. So when we have this, it doesn't mean area, it means the antiderivative of. And we know that dealing with definite integrals, that the definite integral is heavily related to the antiderivative of a function. So we've explored antiderivatives for a few sections. Now we've done some practice problems to kind of get ready for this section and found that if f is an antiderivative of f prime, then if we add c to that function as a constant, that's also an antiderivative, and that's because the derivative of a constant is 0. So when you take the derivative of f of x plus a constant, you get just f prime. This means that there is more than one antiderivative for each function. In fact, there are infinitely many if we add a constant to the end each time. So it's true that just by adding a constant to antiderivatives, that's going to give us all antiderivatives of a function. And that's not necessarily trivial. There could be another function who has, it could be an antiderivative that has nothing like another function, but it is true that we can only get an antiderivative by adding a constant to another antiderivative. So if we want to find all antiderivatives of a function, which you want to do for the indefinite integral, then we can say that the indefinite integral of f prime of x dx is going to be the set, this is set notation here, all functions f of x plus c, where c is a constant, where c is a real number. So that is an infinite amount of functions that we're representing in that notation. And then also know that we're going to commonly write this as f of x plus capital C. So instead of writing brackets f of x plus c, little bar, c a constant like I have in the blue there, we're going to write f of x plus capital C. And capital C does not represent one particular constant. It represents all constants at one time. That's kind of a weird notation, but it's nicer to write that down instead of writing that set notation each time. So C, capital C, represents all constants, and we're going to need that each time we take an indefinite integral, and we'll see some examples of that on the next page. All right, so we're going to go through a bunch of antiderivative rules, and just to show where these rules come from, we're going to show the derivative rule where it's based on, because we're finding a function whose derivative is what's inside of that indefinite integral. Some of these are going to be rules that we latch on to, and I'll point those out as we go. Some of these are really not rules that I think you should memorize. It's more of just things that you should know because of the derivative rules. At this point, you should be experts at the derivative rules. You should know all of those by heart, or at least getting very close to that point. So if you know the derivative rule, you should be able to create the antiderivative rule. So let's run through a few of these. We know that the derivative of a constant is 0. So if I take the antiderivative of 0, I should get a constant. And we could write that as a little constant plus c, but note that that could just be written as any constant, so I'll write that as plus c or just c. We know that the derivative of a line, mx plus b, is just the slope of that line. So if I take the derivative of a number, thinking it's the slope of a line, then I should get out the slope times x plus c. This could be mx plus b. This could be mx plus b plus 1, a different constant. This could be mx minus 7. That plus c represents all those constants at one time. So you may think about this rule as when you have the antiderivative of a number, you're just going to add x to the end of that number. All right, the next one is going to be the really big rule that we have, and that is the reverse I guess I should put that over here, sorry. The reverse power rule. And it comes from going backwards through the power rule for derivatives. That says that if you have x to some power, you can bring the power down out in front and have nx to the n minus 1. So going backwards through that, if I have the antiderivative of x to the n, I'm not going to subtract 1 from the top. I'm going to add 1 to the top. And I need to kind of get rid of that n factor on the outside. And I do that by doing 1 over n plus 1. We've seen this a few times now. We think about the antiderivative of x to the 7th. We increase the power by 1, and we're going to divide by that power 1/8. And add c at the end. Note that this doesn't work if n is equal to -1. That is 1 over x to the first, because we would get a 0 in the denominator, something weird happens. But it works for all other powers of x, and we'll see some examples in a second. The other big rule here that's kind of different than other rules is the derivative of natural log is 1 over x. That's only true if x is greater than 0. So that means that the antiderivative of 1 over x should be natural log, but we need a little bit here that we need the absolute value signs here. Because natural log of x is only defined on 0 to infinity, but 1 over x is defined on all numbers but 0. So in order to make those domains match, we need to have absolute value bars around the x so that we can think about it as an antiderivative. Whereas for natural log, what we have to do is take 1 over x, but not the entire function 1 over x, just the part that's greater than 0. So you're going to have to remember that, one, you're going to have to add c to all antiderivatives, all indefinite integrals. You also need absolute value bars when you take the antiderivative of 1 over x. All right, the next 10 or 12 rules we go through are all going to be just derivative rules and just rewritten in that form. So the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x plus a constant. If you have a to the x, the derivative is natural log of a times a to the x. So the antiderivative of a to the x is going to involve a to the x, but we need to get rid of that constant, so we divide by that natural log. It's like the opposite of multiplying by it. And then add c. Let's do all the trig functions. You take the derivative of sine, you get cosine. So the antiderivative of cosine is sine. The derivative of cosine is negative sine. So the antiderivative of sine is negative cosine. Derivative of tangent is secant squared. So the antiderivative of secant squared is tangent. Derivative of secant is secant tangent. So antiderivative of secant tangent is secant. Cotangent gives negative cosecant squared, so the integral of cosecant squared gives negative cotangent. You have to have the negative there. And same for the derivative of cosecant is negative cosecant cotangent, so that integral is negative cosecant. So you could double check all of these rules that we're doing by taking the derivative of, let's go over here, take the derivative of the right-hand side there. Take the derivative of negative cotangent of x, and that should give you a negative cosecant squared, which is cosecant squared, which equals the thing in the antiderivative. That's always going to be the case. You can kind of check your answer by taking the derivative of that right-hand side. So let's go over last few rules here. We have the inverse trig functions. The derivative of arcsine is 1 over square root of 1 minus x squared. So the antiderivative of 1 over square root of 1 minus x squared is arcsine. If you slap a negative on that, it's now arccosine. And one that's actually going to pop up a lot is this arctangent. 1 over x squared plus 1 is the derivative. So if you have the antiderivative of 1 over x squared plus 1, that gives you arctangent of x plus c. That is one that's going to show up a lot, more so in Calc 2. Then we have our hyperbolic trig functions. The derivative of sinh is cosh, so the integral of cosh is sinh, and vice versa for cosh and sinh. Derivative of cosh being sinh. So again, the point of this list is not to memorize these rules. And if that's what you're going to try to do, I urge you not to. There are a few rules that are worth memorizing. I pointed those out on the first page. But really, if you know the derivative rule, then you should also know the antiderivative rule. It's just going backwards through that process. Once you start thinking about these as, whatever, I think I have 18 or so rules written down here, then you're memorizing too much. You're not really seeing the relationship of these functions as they should be. All right, let's get a couple practice problems real quick just to show what we're doing with this integral, and then we'll do more in the next video. So find the indefinite integral of square root of x plus 1 over x. So note that just as we did with definite integrals, we can write this as the integral of square root of x dx plus the integral of 1 over x dx. And maybe I want to write that as x to the 1/2, just to do that right now. So the reverse power rule, because I have x to some power, says that I'm going to increase the power by 1, and I'm going to divide by that new power, multiply by 1 over that thing. And I should have a plus c here. That's the antiderivative there. And the antiderivative of 1 over x is natural log of absolute value of x. And again, I'm going to do plus c. So writing that a little nicer, 1 over, or I should say, x to the 1/2 plus 1 is x to the 3/2. 1 over 3/2 is going to be 2/3 x to the 3/2. Then I have plus natural log of x, and then I have this kind of plus c business. And now it's important to remember, what is plus c telling us? This is saying that if I add, it represents all constants. So it's saying if I take 2/3 x to the 3/2 plus natural log of absolute value of x, and I add a constant to it, that's also going to be an antiderivative. You can think about plus c is a constant, plus c is another constant. So altogether, this just represents all constants. So we're just going to write it plus c. We don't have to write plus c multiple times. Doesn't really make sense. So our final answer should be 2/3 x to the 3/2 plus natural log of absolute value of x, and then plus any constant from there. Another way to kind of think about this, I don't really urge you to do this, but it does work sometimes, is thinking about, have plus a constant d plus a constant e, and if you have a constant d plus a constant e, that's just the same thing as just a constant, and you could call it c. Again, these are not particular constants. The algebra does not work the same with them. They represent families of functions. I'm going to go back to writing plus c because I think that makes it a little bit nicer. All right, if we think about the definite integral, same function here, the first step using the fundamental theorem of calculus is to find an antiderivative of this function. So I need to write 2/3 x to the 3/2 plus natural log of absolute value of x evaluated from -2 to -1. That means that I need to plug in -1 into this function. and then plug in -2 and subtract. And I realized I was so concerned with the derivative of 1 over x natural log. This is actually not good. This doesn't exist. So this is not a good problem. What I want to point out before I rework this a little bit is to say that you need absolute values around the natural log because you can't deal with natural log of negative numbers, right? So natural log of -1, an absolute value is natural log of 1. That's something we can deal with, but we can't deal it with negative numbers. This is not a good example of that because of the domain issues with the square root. So let me rework this a little bit. We'll just change this to 1 and 2. And we can write this as 2/3 x to the 3/2 plus natural log of absolute value of x evaluated from 1 to 2. And again, now we can just plug in the top bound and in parentheses subtract off, plugging in the bottom bound. And we could simplify from there. At this point, I'm just going to leave that in the interest of time. So note that I didn't use the plus c in that antiderivative. If I did, let's see what would happen. If I had 2/3 to the x to the 3/2 plus natural log of absolute value of x plus a constant c, and I evaluated that from 1 to 2, well, I would take 2/3, 2 to the 3/2 plus natural log of 2 plus the constant and subtract off all of that where I plug in 1. Plus the constant. And you can see that if you don't forget the parentheses, that you're going to have a positive c and a negative c cancel out. And at that point, it didn't really make sense to have that c at all. So really, you never have to add a constant when you're doing a definite integral, but you definitely need it when you're doing an indefinite integral. It's going to take some practice to get used to the plus c in these integrals. We'll do some practice problems in the next video, and it's just going to be something you have to get used to as you go on to the next course, Calc 2, as well.